So far we have been discussing concepts such as first order logic. Subsequently, we moved on to relations and a special relation called functions. And in an attempt to prove claims in the context of logic, relations, and functions, we looked at various proof techniques, in particular sophisticated proof techniques such as mathematical induction and pigeonhole principle. And all along, we have been focusing on finite sets. So you are given a set of finite size, and with respect to that, we started focusing on a formal way of representing elements with some specific properties. That's when we brought in first order logic, and subsequently, we moved on to predicate logic, and so on. Then we made some interesting claims to prove that we looked at sophisticated proof techniques. Subsequently, we moved on to something called cross product, and relation is also a set which is a subset of a cross product. Then we started defining a couple of properties with respect to relations. Then we looked at special relations such as equivalence relations and partial orders and so on. Now what we will do is we will move on to infinite sets, and so far we did so much about finite sets, but there are many interesting sets that we come across in mathematics and computer science. For example, the set of natural numbers, set of real numbers, and they are all infinite in nature. In the context of computer science, if you see the number of C programs, number of C++ programs, number of inputs to the sorting problem, they are all infinite in nature. So it makes sense to study the infinite sets because it has got relevance in the context of computing and mathematics. Not just the mathematics field. If you look at theoretical computer science field, almost every well-known sets that we come across are infinite in nature. So what we will do is we will see how to prove a set is infinite, and just like the way we count finite sets, we say this set has got cardinality 10, 15 and so on. Can we count infinite sets? Can we compare two infinite sets? Just like the way we compare two finite sets, can we compare two infinite sets? And many interesting things. So to start with, let's look at uh, how to define a finite set. So we say a set A is finite. So if there exists a bijection from 1 to k to the set A. And what is k? K is the cardinality of this. So you say a set is finite if there exists a bijection from the set 1 to so on up to k to the set given to you. What is k? K is precisely the cardinality of this. Suppose you are given A as say 1, 2, 3, 4, 5, 6. So what it says is to say that this one is finite, all that I need is I need to establish a bijection from 1 to k, where k is the cardinality, to the set. Now you can simply map 1 like this, you can do it, and set could be anything. So in general, you have got 1, 2, so on up to k. On the other side, A has got A1, A2, so on up to AK. Then you can establish a bijection like this. If such a bijection is not possible, then you say the set is infinite. So if there exists a bijection from this to this, otherwise A is infinite. Which means what? There does not exist k such that you get to see a bijection from 1 to k to this. Or every k that you come up with, you don't see a bijection. Fine? So this is relatively straightforward. Now, with this, we want to know, can we prove things like set of n, set of natural numbers, the set of real numbers, and the number of C programs and number of inputs to the sorting problem. So all that, how do we show? How do you prove them that all these sets are infinite in nature? We will define one more definition which is suitable for infinite sets, then we start looking at these case studies. So we say a set is infinite if there exists a function f from a to a itself such that f is 1 to 1 and f of a is a strict subset of a. So the first definition tells you how to define finite sets. This will tell you how to define infinite sets. I will give you some motivation or the intuition behind this. Look at finite sets. So focus on finite sets. For example, you take say a to be 1, 2, 3, 4. I ask for a function from a to a such that f is 1 to 1 and f of a is a strict subset of a. So I need a function which is 1 to 1 and f of a is a strict subset of a. For example, this has to be 1 to 1. So let me map something like this, because for each of them the image has to be unique, right? You cannot have two different elements mapping to this. Now 4 I cannot map it to this because f of a has to be a strict subset of this. If you map 4 to 3, then 1 to 1 is violated. So now this shows that you look at any finite sets. For any finite sets, this is not possible. Meaning asking for a function satisfying this is not possible. So you are asking for a function from a to a such that f of the function is 1 to 1 and f of a is a strict subset of a. And question is, can we find f? Can we find such a function f? Answer is no. So no function f exists satisfying the above condition. So what does that mean? Which means you look at a function from a to a and you ask for 1 to 1. Function is from a to a and you ask for 1 to 1. So which means, so any one-to-one function from A to A is also bijective. Correct? Which is why we are unable to find one-to-one satisfying this. So the image has to be strict subset of A. That's not possible. So what does that mean? For a finite set, if you ask for a one-to-one function, that one-to-one function will also be bijective. So which means I relax this. I am interested in asking for a function which is one-to-one and f of A is a strict subset of A. Now I relax this, meaning now focus on infinite sets. In the context of finite sets, it's not possible. Focus on, say, infinite sets. You ask for a function from natural numbers to natural numbers. Okay. So now let's assume 1, 2, 3, 4 and so on. 1, 2, 3, 4 and so on. What I'll do is I'll map 1 to 2, 2 to 3, 3 to 4, 4 to 5. So f of x is equal to x plus 1. If I do that, you see that this 1, there is no pre-image. Correct? Which means f of A is a strict subset of A, or f of natural numbers is a strict subset of natural numbers, and the function is one-to-one. So no two elements in the domain is mapping to same thing, right? If you look at x, x is mapping to x plus 1. If you look at y, y is mapping to y plus 1. And x and y are different, so x plus 1 and y plus 1 are different. So f of A is a strict subset of this, and the function f is one-to-one. So it turns out that in the context of infinite sets, one can ask for a function which is one-to-one, satisfying this condition. So interestingly, it has become a definition as well. So for finite sets, such a thing is not possible. Now shift the domain. Can I ask for a function which is one-to-one and satisfying this? Answer is yes. And interestingly, it has become the definition as well. So which means to show that something is infinite, you ask for a function from the set to itself. And that shows that and what is the property of the function that you ask for? It has to be one-to-one and satisfying this. And that shows that there are many more elements. This is what this says, right? F of A is a strict subset of A, which means you can keep seeing more and more elements in the set A. That naturally brings infiniteness into the picture. Okay. So now we shall show that the set N is infinite. Just now we have seen through the definition 2 that there exists a function which is one-to-one from n to n such that f of n is a strict subset of n. We can also use the definition 1 to show this. Proof by contradiction. Suppose n is finite. Okay. And let's use the definition 1. So definition 1 is a set A is finite if and only if there exists a function f such that f is bijective and the function f is from A to Okay, and what is k? K is the cardinality of this. Fine, and it's bijective. Either you can write a to 1 to k or 1 to k to a. That's fine. So it is, suppose n is finite, then there exists n such that n represents the cardinality of n. So which means small n is equal to cardinality of this. Fine. So now you have a function f which is from 1 to so on up to this to n. You can write this way or that way, but let's stick to this. Okay. Now you have 1 to so on up to this moving to n. Fine. So which means if you look at the function, this is the first natural number, second natural number, so 1, 2, 3 and so on. This is the third natural number and so on. So you see that 1 is mapped to this, 2 is mapped to this, 3 is some function. Okay. And some mapping. It could be 1 is mapping to A1 or 1 could be mapped to A2, so it could be anything. So what I'll do is, now you know what is f of 1, you know what is f of 2, they're all natural numbers, correct? You know what is f of 3 and so on up to what is f of n. Fine. And now I'm going to cook an element. So consider this element. So x is equal to max of say f of 1, f of 2, so on up to f of n. They are all here, f of 1, f of 2, they are all here, they are all natural numbers. You take max out of that. With that, you add some number, say plus 1. You can add plus 10, plus 100, you add some number. Now, clearly, x is a natural number. Correct? Suppose the max is 100, what you get is 101. Suppose max is 10, what you get is 11. So x is a natural number, and but there is no pre-image for x. So as per f, there is no pre-image for x, which means f is not onto. There are elements in the codomain for which pre-images are not there, which means the function is not onto, and that's the contradiction. And which means there are many elements over here for which there is no pre-image, which means the function is not onto, and you get a contradiction. Why are we arriving at this contradiction? This statement follows from this one follows from this, and we are cooking an element based on the function that we have taken. And if you go back and all this, because each of this follows from the previous statement. So which means this contradiction is triggered by this wrong assumption, and therefore our assumption is wrong. So this implies that n is not finite or n is infinite. So to show that it is infinite, we assumed it is finite, proof by contradiction. So somewhere I should get a contradiction, Then if it is finite, apply the definition. It says there exists little n which represents the cardinality of the natural numbers such that there exists a bijection from 1 to n to this. And focus on the bijection. Now I am cooking an element which is a natural number for which there is no pre-image, which means the function is not onto. And so we are getting a contradiction. We started off with saying there exists a bijection and so on, and we arrive at that such a function is not onto. And why did this contradiction arise? It is because of our wrong assumption. So therefore n is not finite, so n is infinite. You can use the other definition. Other definition says there exists 1 to 1 from n to n such that f of n is a strict subset of n. That's what we did before, and you can use that or this to show that n is infinite.